Hi everyone, welcome to lecture 7. This is spatial estimation. So the topics of this lecture will be spatial sampling, spatial interpolation and prediction, and some core areas. So to start off strong, what is spatial interpolation? Spatial interpolation is predicting variables at unmeasured locations based on samples at known locations. So why would we want to interpolate? There are an infinite number of potential sample locations, but we can't always measure these sample locations. Some of these reasons may be time, money, or just impossibilities, whether it is a physical place that's impossible to get to, whether there are legal sanctions around it that don't allow researchers or individuals to go take these samples. So when we interpolate, we can do this for changing cell sizes, we can do this for missing or unsuitable data, and we can also do it for data that's past a certain date or rapidly changing data, such as temperatures. When we do spatial prediction, this is similar to interpolation, but it uses some variables that actually predict other variables. An example of this is elevation and temperature. We know that as we go up in elevation, we typically go down in temperature, so we can predict that an increase in elevation will decrease temperatures. For sampling, the goal is that we want to provide some reliable estimate without the need to measure every single place. This really helps in terms of cost as well. You can imagine that it's pretty expensive and pretty time-consuming as well to take samples at every location that you may be interested in. So, where do we take our samples? There's costs of access and there's efficiency that go into this measure. We also have to consider how many samples we want to take. There is such thing as law of diminishing returns. The more you take, it doesn't necessarily mean the more that it pays off. So the question we have is, how do we maximize the accuracy of our estimates while we minimize the number of samples that are required as well as the cost of sampling? So there are a few different methods. We have systematic sampling. This is pretty easy. These samples are uniformly spaced and they're fitted at XY intervals, typically using parallel lines. The advantage is this is easy to understand. The disadvantage is that every point is receiving the same attention, and it's pretty difficult to stay on lines all of the time. In addition, there may be bias. So whatever is the first point that you choose as the location that we're then going to do our systematic sampling by on our XY grid, there could be a bias there, right? This bias is where an estimate obtained by sampling is different from the true underlying value. An example is that if your thermometer is leaked from mercury, all the readings may be 5 degrees too low. That's a 5-degree bias. So why should systematic sampling sometimes lead to a biased estimate? After all, we are covering the entire area. So here's a thought experiment for you. Imagine we have a landscape with hills and regular distances between each of those hills. We decide to use a spacing between sampling points that is the same as the distance between these hills. Let's say that we pick a point at the top of the peak and then we start sampling. Well, our result is going to be biased. We'd say that the mean elevation in the area was that dotted line, but the solid line is the real mean elevation. If we wanted to pick a different starting point, we'd get a different but still biased value. So now, instead of overestimating like we did in our last example, we are underestimating what the average elevation for the area is. But maybe we get lucky with our systematic sampling. Perchance, we might choose that correct mean elevation as the starting point. In a thought experiment like this, you can see it's pretty easy to see where that sampling point should be, but it's not very likely in the real world that we choose the right first choice. We'll still get a bias if our sampling interval is a multiple of the landscape's periodicity. So, with systematic sampling, there's always a risk of bias, and this is something to keep in mind. It's not a wrong way of sampling, but there is a high risk of bias. So how do you know if the bias is there? You probably won't. Given only systematic sampling, it's not possible to test whether bias has occurred. It can be tested using other data, but then why not just use that other data? So we might again get lucky. Bias will decrease as the differences between our sampling intervals and the interval between those peaks increases. So the more we sample and the more difference we select between those sampling points, the more likely we are to decrease that bias. Random sampling, however, is unbiased because it is random. There are a lot of points, and the systematic variation in the environment won't be a problem in this case. If there is no periodicity in the sample, there won't be a synchronization that will then give us bias. So random sampling is based on selecting points from a random number process that we plot on the map and then we visit. So here on the right-hand side, you can see this isn't nearly as uniform as our systematic sampling. The advantages are the decrease in bias. The disadvantages are that it doesn't do anything to distribute samples in areas of high variation, and it's also difficult to explain, and still, location of points may be a problem. It may be impossible to access some of those points. So we have something called adaptive or stratified sampling. This is where more sampling occurs where there's more variability, but you need to know knowledge of that variability beforehand. So this is more of a two-stage sampling system. You have to know the landscape or the area you're sampling first, and then based on that choose where is there more variability than other locations and plan accordingly. Your advantages are that this is more efficient, it's homogeneous for areas that have few samples, and it's better representation of those variable areas. Your disadvantages are that you do need to have prior information on the variability throughout that space. So then you have adaptive sampling. Adaptive or stratified sampling, again, these schemes are similar to those used in non-spatial fields. This is like opinion polling. You identify groups that are likely to differ on the questions between them, but be relatively homogeneous still within the groups. They are randomly selected individuals with numerically important groups. So with adaptive or stratified sampling, these can be used for continuous data or discrete data. For continuous data, it's using estimates of variability to allocate those samples. With the discrete data, it's allocating samples to cover land classes. Once your strata are determined, either random or systematic sampling can be used within each of those strata. So this is an example here for sampling. If you have fewer researcher decisions, that is the high end of this. Many researcher decisions is the low end. You may have more general applicability, or you may have more specific applicability, and you may have lower efficiency or higher efficiency. And on the right-hand side here, you can see how this relates to the different type of sampling methods we have. With random sampling, we have fewer researcher decisions and more general applicability, but it's lower efficiency. With adaptive or stratified sampling, there's a lot of researcher decisions that go in, there's a lot more specific applicability, and it's higher efficiency. Systematic sits somewhere in between. Then we have cluster sampling. So cluster centers are established random or systematic or adaptive. They are subsamples arranged around each other. Each of these clusters here in this image represents one singular sample. You plot these on the map and then you visit each sample. The advantages are that there are more accurate measurements at each of the sampling points because you're taking multiple samples around a main area, right? The disadvantages are that fewer sample points are selected for a given amount of effort. So you may validate these certain chunks of samples that you see here, or these certain clusters of samples, but all of that area in between goes unsampled. So you can see here our systematic clusters, our random clusters, and our stratified random clusters. We can still take in those different types of applications where it's systematic, stratified, or random, and put it into a cluster analysis. So when do you choose to not cluster sample? You would choose not to if it is a low variability area and a single sampling point would suffice. So if it's a flat area, for example, if you're looking at terrain, you wouldn't be interested in doing a cluster sample. You're not going to get many differences between those samples. When would you want a cluster sample, though? You would want to do it in an area where a cluster of subsamples will give a more accurate estimate for elevation in the area than one singular point would. Think back to our thought experiment with those mountains and valleys. That would be a great example of when we may want a cluster sample. So note that with the exception of systematic sampling, estimates you get should be unbiased. This means that the average values obtained should be all from methods of the same. What tends to differ the most among those methods is those estimates of the variability. So the spread of variability will change, but the average values stay the same. This is telling you that there's no bias, but there's a change in the efficiency depending on how you are sampling. So for sampling, which method do you want to use? Ultimately, this depends on what the goal of your sampling is, what the nature of your study area is, and then what resources you actually have to apply to your sampling. The goal of sampling is ultimately statistical analysis, right? If you want a relatively simple statistical analysis, random may work, but you're going to have a low power. If you use systematic sampling, you have to be able to prove that there isn't any bias, which is difficult. Cluster sampling is going to require pooling or combining subsamples within that cluster, so you only want to make that extra effort when you're using subsamples substantially, and that increases the accuracy of the sample estimate. Adaptive sampling can work well, but only if you're able to provide a good basis on which you made those decisions. So for the nature of your study area, the size of your area affects the logistical difficulty of getting to sampling sites. And this makes sense, right? Large area is going to be more difficult. Small area is going to be easier. So maybe for a large area, you want to do cluster sampling or adaptive sampling, whereas for a small area, random or systematic may work. You also have to take into account how variable your study site is and how that variability is distributed. When that variability is concentrated, adaptive sampling may be most effective, such as the Grand Canyon. When it's widespread, random sampling might make more sense, such as small craters on the moon. If you have a lot of resources, you can use less efficient methods, but you may have very limited resources and you might have to use other approaches. These logistical difficulties involved in reaching certain locations also have an impact on whether or not you want to use cluster sampling. So which sampling method is best for this example? You have your original surface, and then you have your applications of systematic sampling, random, cluster, or adaptive. So go ahead and think on what you think is the best sampling method for this example. Before we go on to the next slide, because again, this is an asynchronous course, I'll bring us back for a moment. If you look at the original surface, we see there's a lot of variability, and it seems to be a large scale. There seems to be a lot of room on this map. So systematic sampling, again, it doesn't really give any specific attention to any one location. It's all based off of an XY grid. This might not be the best. Random sampling is always in some way a decent approach, at least a decent first approach, but we see that where there's all this variability within the map, we don't really focus on it. In our cluster sampling, we see that we have maybe one or two areas of high variability over on the eastern aspect of this image, but then we don't really have a lot of other clusters that focus on that. Adaptive sampling in this case might be the best, but with all of this said, we have to take into account our resources. We also have to take into account how likely it is that we can actually get to these sample points. Those areas of high variability that look like they're very well charted by that adaptive sampling may not actually be accessible to us. So this isn't really a trick question, but it's more of a thought question again of what makes the most sense based not only off of the information we want and the amount of variability that's in that area, but also the resources that we have to apply. So now going into interpolation and prediction, we're using the point data to generate complete coverage is our method. Interpolation is when we make a map, we don't want to have a lot of gaps in it, so we want to fill that data in some way where the data doesn't exist. A main approach is interpolating what those missing values are, using the surrounding values around that point of interest. There are many methods to interpolate. Methods differ in the weighting and the number of observations used. These different methods will make different results for you. There's no one method that is the best way to go about it, and your accuracy is judged by withheld sample points. So when you interpolate and you pull back a few of those sample points, you see how much does my overall value or my overall assumption change. So all of these methods combine information about the sample coordinates with the magnitude of the measurement variable to estimate the variable of interest at an unmeasured location. It's a very wordy way of saying interpolating is basically taking data that we know to try to understand or assume data that we don't know between it. So this is an example used to demonstrate some of these methods, right? You can see that there are a bunch of points over here, and on the right-hand side of the screen, you can see the interpolation between it. One of these examples of interpolation is the nearest neighbor or Theisium polygons interpolation. This assigns values equal to the value found at the nearest sample location, hence the term nearest neighbor. Conceptually, this is the simplest because it only uses the closest point. So this right here is an example of those polygons. Again, you see all of these points on the left-hand side. On the right-hand side, you can see that we have our clusters And then we have our more open expanse based on those points. We just take the nearest neighbor and assign a value between it based on that. This is what it looks like applied to an actual map, both a raster and a vector. Then we have fixed radius, or local averaging. These are cell values estimated based on average of nearby samples. So not just nearest neighbor where it's this is that, we're going to put the two together and make a guess. We're actually averaging the nearby samples generally. The samples used depend on what the search radius is that you put in. Any sample that's outside of that circle or is not used in the average. Any average that, or any sample, that is within that radius we choose will be used in the average. For this, we have to specify the output raster grid, and a fixed radius circle is centered over a raster cell. That circle radius typically equals several raster cell widths, and this causes neighboring cell values to be pretty similar. Typically, we have several sample points used in this type of interpolation. Some circles, because of this, may not have any points, so the search radius is very important. If it's too large, it may smooth too much data, and if it's too small, some circles may not have any data at all. So this here shows you what that fixed radius application looks like. We have our input on the left-hand side and our output on the rest. We see that we have a 0.6 and we have a 0.8 that fall within this raster grid cell. So the output is the average of the two, which is 7. And it continues on for the rest of these input circles. You can also see here our fixed radius sample size is this circle. The output value of those samples is applied to the center point of a raster cell. So we have our input sample layer and then our interpolated surface based on that. Then again, we see on the left-hand side our original surface. We've seen this figure a few slides back. On the right-hand side, we see the interpolated surface using that fixed radius approach. So you can see it's not that it looks insanely different, but it does look different. We can see that where there's high variability, all of those points get clustered within the same radius. And when there's still variability, but lower variability, there are some circles that just don't have any points in them at all, or they all go within this very oddly shaped scheme that doesn't give us too much information. So radius size is very important. This here again is the original surface on a raster looking, and this is it on the fixed radius effect still on a raster. This is kind of that output that you can imagine. So we still see, it looks like this might be a body of water, right? Or a very low elevation area, this black line that's kind of moving through. In our fixed radius application, you can still generally see that that's there, but there's not much resolution. Then we have inverse distance weighted, or IDW. IDW estimates values at unknown points using the distance and values to nearby points. IDW is meant to reduce contribution of one known point to that interpolated value. So the weight of each of those sample points is an inverse proportion to the distance. The farther away that point is, the less it is weighted so that it does not too heavily define that unsampled location. So you don't need to know any of this. You just need to know that this is the general equation for IDW. This is somewhat what it looks like. There's a weighting basis here. I is the number of those neighboring points that you choose, and you have to select n. So n is not data, it's a user-selected exponent, which is basically your weighting. And here I'm actually going to just skip us through that because you don't need to know this. For IDW, these are factors that affect the interpolated surface. The size of the exponent, which is n, that's going to affect the shape. A larger n means that the closer points are more influential. A larger number of sample points, which is I, results in a smoother surface. Let me take us back. This is IDW, the original surface on the left-hand side. And this is IDW using linear and 6 nearest points. On the next slide, we see it, skipping through here, we see it squared and at the 12 nearest points. So you can see just between the two of these right-hand figures, how different it being linear or squared is, and how different having 6 nearest points versus 12 nearest points affects that visual. This is another example of IDW for different values of n and I. Our original surface is in the top left corner, and then we have variations of n and I that increase either n equals 1, I equals 6 up here in B, or n equals 2, I equals 6 down here in C. You can see even just between the two of those how that visual changes. And then especially when n is equal to 2 and I is equal to 20, how different that is, even just from C and B. So splines are functions used to interpolate along smooth curves. You may have heard or utilized splines in some sort of statistics to also interpolate values. The name is derived from the drafting tool, which is a flexible ruler, and that helps to create smooth curves through several points. You can force a smooth line to pass through these desired sets of points, and is constructed from a set of joined polynomial functions. So this is an example here of some lines and a one-dimensional spline. You can see the vertices, you can see where they connect and make this kind of jagged looking line, and you can see where that smooth line or spline exists. So here again is an example of the original surface and then a spline interpolation. You can see that it does pretty well handling all these small variabilities within it. This is again the original surface and then the spline interpolation of that surface. Another method is called trend surface. This is used to combine things that you do know to estimate other things that you don't know, like most interpolations. We may know the coordinate of the raster cells, and then we might want to predict values for the cells we haven't sampled. This here is an example of the equation. It estimates the b's using a least squares fit, and then it applies it to pixels with unknown values. So here is your visual of trend surface on the left, and then the actual application on the right. Oop. For the trend surface, such as with polynomial regressions, you can add additional powers. And when the number of those terms increases, and there are more complex surfaces that can be described. So this is more known data to fit. Again, when your number of terms is increased, you can describe more complex surfaces because you're covering more area. Typically, this won't work well on very complex surfaces though. So you can add terms for additional variables that may help make more accurate predictions, but the trend surface itself may not be that great for a very complex surface. Spatial prediction looks at differences from interpolation. It's a statistical fitting process that that's used rather than a set algorithm. So this is statistics versus an algorithm. It's going to use independent variables as well as the locations to try to estimate unknown variables. So here we're going to focus on continuous variables instead of discrete or categorical. We can first look for spatial prediction on Tobler's first law of geography. Everything is related to everything else, but near things are more related to each other. And why does this tend to be true? Well, think of it. In areas that are near one another, they typically share common factors such as similar soils, similar amounts of rainfall, similar amounts of shading. In biology, people that are nearby one another may be related to one another. And as you get further apart, those common factors are less likely to be shared. Think about types of currencies. Think about cultural norms. The further that you are away from one location to another, the more variance there may be between those. So one of the consequences of Tobler's first law of geography is the frequent observation of spatial autocorrelation. So over here in layer 1, these nearby cells tend to be similar. This leads to a positive spatial autocorrelation. In layer 2, though, those cells are pretty random, and therefore there is no spatial autocorrelation. There's also something called spatial cross-correlation. This is cross-correlation in between two different layers. The corresponding cells in layer A and layer B tend to have similar values, which leads to this positive spatial cross-correlation. Another spatial predictor is Moran's I, and this is used pretty heavily, especially kind of in, I won't say in introductory GIS, but it is a tool that's used pretty heavily as it's pretty straightforward to utilize. This statistic is for autocorrelation. It'll take a value from -1 to 0 and from 0 to +1. The closer it is to a +1, the more correlation there is between neighbors. The closer it is to 0, this is indicating no spatial autocorrelation. To calculate it, you need to define what is adjacent. This is more difficult to do for vector data than it is for raster. A raster is going to use a rook or a 4-cell, or a king, which is an 8-cell pattern, to look at what is adjacent. So this here is the statistic itself, or the equation for the statistic. What you need to know again is that positive means positive autocorrelation, negative means negative autocorrelation. So if it's a negative value that you get from this equation, it means that the nearby values are very different. If it's positive, it means they're very similar. This z value is the values within the raster cells. the W's are the weights, either a 0 or a 1, used to define those neighbors, and n is the number of cells that we're using. Again, you can see over here this equation, and this is kind of giving you an example of using the rook's case versus the king's case. I won't get into this, but I'll leave this for you guys to pause on if you want to better understand the actual mathematics behind it. So in ArcGIS, to actually utilize this tool in a much more simplified way than the last slide, you can calculate Moran's eye using the spatial autocorrelation tool in ArcGIS. You'll see it's also called global Moran's eye. The level of autocorrelation can have an impact on the degree of pseudoreplication as well. Autocorrelation can cause samples to violate assumptions of independence that are inherent in most statistical analyses. So something that you'll notice with all these versions of interpolation and prediction, there is no one cookie cutter approach. You have to be meaningful and intentional with what it is that you choose based on the data that you have. Then we have something called kriging. This is similar to the IDW approach. It uses the minimum variance method to calculate weights rather than applying some arbitrary or less precise weighting scheme. The advantages are that in addition to filling in the gaps, you can also estimate how precise those predictions are. So kriging using lag distance, again, we see here an example of some variables that go into our equation. Zi is a variable at a sample point, where hi is the distance between those sample points. Every set of pairs, either Zi or Zj, defines a distance hij, and is different from the amount of Zi minus Zj. The distance hij is the lag distance between point I and point j. So you'll see here, Zi minus Zj in this table in the very top row is equal to 4, but hij is equal to 7. So again, it's not the difference between Zi and Zj, it is a set of points that is between those sample points. There's a subset of points in a sample set that are given lag distance apart, and we can use that subset to estimate how variable points are at a given distance. Where Zi is the measured variable at one point, Zj is another at h distance away. N is going to be the number of pairs approximately h distance apart. We multiply by half so that we have the same distances and values twice, because each point shows up once as Zi and once as Zj. Semivariance may be calculated for any h, and when nearby points are similar, it's small so the semivariance is small. High spatial autocorrelation means points near one another have similar z values. Because again, autocorrelation, we're saying, oh, these are similar, these are almost the same. So if it's a very high spatial autocorrelation, it means that those points are pretty close by. So when you calculate semivariance of a particular h, often you have some variance. You plot that semivariance of a range of lag distances, and it's called a variogram. So that's an example right here in the top right corner. Oop, let me take us back. This here is an image of an idealized variogram, all right? You have your semivariance on the left-hand axis, you have your range on that x-axis, you have this nugget over here, and then you kind of see where that plateau occurs across the sill. So you have a set of sample points used to estimate the shape of the variogram. Then that variogram is made. A line is fit through those set of semivariance points, and the variogram model is then used to interpolate that entire surface. So this here is now your actual variogram. You see your estimated semivariance and then your model fit semivariance. You use the model to make those predictions. These are the actual points, the more spiky ones, and you have the actual model fit semivariance, which is that more smooth line. This is now the actual visual interpolation of kriging. You can see that this is doing a pretty nice job at looking at the original surface versus its interpolated values. Again, another visual here of the original surface and then the krigged surface. Remember a few slides back that we were looking at one of our interpolation methods, and although we kind of saw this river or very low elevation point, we didn't really have a lot of resolution on it. This krigged surface does a much better job in this case. With kriging, we can also calculate the variance of our estimate. So that means we can state the level of confidence we have about each estimated value, which is really great. So which interpolation method do you think worked best for this example? This is another kind of thought experiment. Just go ahead and look at your original surface and choose some of these methods that you think are best. We have Thesian polygons, fixed radius or local averaging, IDW, squared at 12 nearest points. We have trend surface, spline, and kriging. So if you want to do interpolation in ArcGIS, you want to go to the Geostatistical Analyst toolbox. You can use either individual tools in this toolbox, or you can also go to this Geostatistical Wizard. This here is an example of the Geostatistical Wizard and kind of what it would look like. You see your different methods, interpolation, interpolation with barriers, deterministic methods. Then you have your input data set, your data field, and your weight field, based on whatever the selection is that you make here on the left-hand side. So these here are some core areas that we've selected, D, E, and F. You can see how those radii around them, or I think that's the right word for it, radii, kind of vary across what we've selected as core areas. Core areas are defined as primary areas of influence for an organism, object, or resource of interest. They're commonly used when we have observations on sets of objects and we want to identify regions of high density. Maybe we want to see regions of high crime, high wildlife, high pollutant detection, or pollutant existence. And then we can derive regions or density fields from that set of sampling points. So here, the question is, what is the core area? Is it D? Is it E? Is it F? The answer is we have to choose. We can identify this using a mean circle approach, using hull or minimum convex polygons, or using kernel mapping. So mean circle or the centroid has the average of xy value coordinates. The mean distance circle is the mean distance from that centroid for each of those sample points. So you see we have our mean distance circle here, our maximum distance circle. We have our mean center with most of those points around it. If the points are normally distributed, or bell curve, right, then you can calculate probability of encounters at a given distance. These work best when there's no directionality to your system. What if we do have directionality, though? Then perhaps we want to use a concave or convex hull. So convex, it's completely objective. Concave, there's some subjectivity. These are our original points, and then you can see concave versus convex, how it's kind of applied. These are widely used because they're simple to develop and interpret, and there's an objective or no subjective aspect to it. This does not work very well where there are outliers, though, because even one single point outlying can have a very big impact on what those hulls look like. They also ignore clustering, so you lose information on density or intensity of use. Then we have kernel mapping. So this is going to use distributional information, which is similar to the mean circle approach, but it allows irregular shapes that are similar to that convex hull. To do kernel mapping, you specify the bandwidth, you establish the distribution for each of those entities, and then you combine those distributions into a composite density to select what the densest areas are. So this here, you sum the total for a smooth density curve. This is many sample points that are plotted individual and composite density distributions with an H of 2.2. What you need to get from this is just that we're summing the total for some smooth density or some smooth surface value. These are our density functions on the y-axis and our sample locations on the x. So we have a medium H or a medium bandwidth, a low H, and a high H example here. D through F are 90% density regions, so those are on the bottom of this figure here. A, B, and C are variations of our bandwidths. So you can see here, just changing that H value has a really big impact on what we find basically interesting or what we cluster. So in summary, in this lecture, we've covered sampling, the systemic, random, and adaptive approaches, and those are utilizing either with clustering or without clustering, and when one might be preferred over the other. We've also discussed interpolation, such as Artesian polygons, fixed radius, IDW, spline, trend surfacing, and kriging, as well as the semi-variograms that come with it. You've also learned what Tobler's first law of geography is. Things nearby each other are probably more similar. You've learned about spatial autocorrelation and cross-correlation, and you've learned a little bit about variograms. Lastly, you learned about core areas and how we can measure core areas or identify them using mean circle approach, convex or concave hull approach, or the kernel approach. So with that, you have now finished lecture 7. Make sure that you are checking in with your syllabus to see where you are in terms of your tutorials and your assignments. You should definitely be considering and probably working on your final project by now. If you have any questions, especially about things like the semivariograms, mean circles, IDW, Moran's I, and such, those are great questions to put in the Piazza and have discussion with your peers. With that being done, good luck with your tutorials, good luck with your assignment, and good luck with your final project.